Hi, welcome back everyone to the second part of this session. Hi Federico, welcome to the workshop. It's a pleasure to have you here. So let me just briefly introduce Federico. Federico Mattei is technical leader at IBM and also IBM Quantum ambassador. And today he's going to introduce the IBM Quantum environment, the growing quantum performances and the quantum network. So I think Federico, you can start. You can share your screen.
Okay, great. So
perfect. We see it.
Print?
Yeah. We see it.
So thank you very much. I would like to thank all the organizers also for this the meeting of this year. We participated in the last 4 conferences, and it is always a pleasure to be part of this annual meeting. So I'm Federico Mattei. I'm working from IBM, and IBM is studying quantum computation since the early 80s. And we are working to develop superconducting universal quantum computers. And we also developed a software kit called Qiskit, Quantum Information Software Kit, which is open source, so is publicly available to program our system. We released on internet, so we public access the first quantum computer in 2016, and now we are growing. Just 1 month ago, we had our annual Quantum Summit meeting, in which we presented all the evolution of our system, of our software stack, and also on our network. So I will go through these announcements so that we can see together how is proceeding the evolution of IBM quantum computers. So let me start from this equation, which is the way in which IBM would like to measure the performance of a quantum system. So we are not speaking just about the hardware or the processor, but we are speaking about the whole machine and also the software which is surrounding quantum computing. And as far as we will see, in particular in the speed part of this equation, we are working strongly to connect the quantum computers with classical computers, because we believe that the real quantum advantage will be achieved as soon as possible if we make quantum computers and classical computers work together at best. So in this equation, you can see that the performance of our computers and our systems are measured with these 3 quantities. The first one is scale, which is measured by the number of qubits. Of course, as I already said, we are working on universal quantum computer or gate-based quantum computers, as you have heard. So these are not annealers qubit, of course, but it's a quantity which is easy to measure and also easy to compare with other approaches. Then we have quality. The quality of our systems are measured by quantum volume, and we will see which kind of quantities are inside this quantum volume contribute to measure this quantum volume. Of course, this is not a standard measurement. It is a proposal which we proposed to the market in 2019 with a scientific paper. And we hope that we will have as soon as possible a standard in order to measure this kind of quantity for all the quantum systems. Aside to this, we measure speed. It is a new quantity what we introduced this year. We measure it in CLOPS, so circuit layer operation per seconds. And we will see in this presentation how software and also classical computation helps to improve this kind of quantity. So in this chart, you can see summed up which is our achievements in the last years. So about scale, we are growing the number of qubits, and just 1 month ago we announced the Eagle system, which passes the number of 100 qubits per processor. It has 127 qubits. Looking at the quality of our processors, at date we have a processor with 128 quantum volume, and our target is to reach 256 quantum volume in this year. So we have few days to reach this goal. Regarding the speed, as I already said, we introduced this quantity just this year, so we can just infer what could be this measurement during the previous years. But for the moment, we have 1,044 clocks, and we hope to improve it year by year in the following one. So let's focus on each of these quantities. Let's focus on scale in particular. And here is the roadmap that we presented last year about the evolution of our hardware processor in terms of number of qubits. So starting from 2019, we are beginning to measure this generation of systems. Of course, I already said that we published our quantum computer since 2016. At date, we had just a 5-qubit system. But now, of course, we are going forward. We achieved the goal of this year, so we presented the Eagle processor 127 qubit, and the next year our goal is to reach 433 qubit with the Osprey processor. The most important goal for our side is the Condor processor in 2023, where we will surpass 1,000 qubit, and it will be really an important goal because with more than 1,000 qubit on a processor, we will be able to do error correction, and probably for some kind of algorithms it could be possible to reach quantum advantage. So we hope to reach this target soon. Of course, we will not stop with 1,000 qubits for processor, but our idea is to go forward in order to build 1 million and beyond qubits for each system. As I already said, 1 month ago, we announced Eagle. We had the possibility to surpass 100 qubit for processor, building this chip on different layers. So on one layer we have the qubits, and on the other layer we have the resonators, and so we'll have the connection and the readout part. These are the connection and the picture of the sides of our processor. As you can see, we have this something like an hexagonal topology. It seems to be the better trade-off between the connection, the connectivity between the qubits. Qubits are, of course, the circles with the number inside, and the connection are the white slash between one circle and the other. I'm saying that it is the better trade-off because experimenting more connected situations, we will face problems like crosstalk between qubits, and so it seems to be the better situation in order to have a good coherence time and also a good connection between qubits in order to do entanglement for the algorithms. So that's the current situation. Let's turn to quality. So as I already said, we presented our proposal to measure the power of quantum computing using this quantity. This quantity is composed by several measurements that we can do on a quantum system. Of course, the number of qubits is just one component of this quantum volume. Of course, we have coherence time there, we have crosstalk, and we have several kinds of fidelity that we measure in our system, the measurement fidelity, gate fidelity, initiation fidelity, and all the rest. So all these components are summed up in this quantity, which from our point of view is the best way to measure the real power of a quantum computer. From the quantum volume point of view, as I already said, we are waiting for the 2056 processor with quantum volume for processor. But a very interesting announcement has been done in the Quantum Summit. In particular, we announced that we surpassed 1 millisecond for the coherence time on our processors. And we also announced that we surpassed 99.9% in the gate fidelity. So these are two important parameters which are then converted in the quantum volume measurement. This is the plot of the quantum volume of our system during the last 4 years. As you can see, we doubled the quantum volume each year. Last year, we did 2 steps. And so we hope that we can do something like more slow also for quantum computers, and we hope to be able to double the power of our quantum computers in terms of quantum volume each year. Then let's turn to the speed part, which is the last one that we announced, the last measurement that we announced, but it is very important also from a productive point of view, because when we are going to we will use quantum computers in production, in the business or in the research, the speed component, it will be very important, in particular on some kind of business, for example, the financial services and also the logistics, in which you have to do calculation very quick. So this is the quantity, the circuit operation per second, and it is an important measurement that we will continue to use in the next year. As I already said, it is a crucial component in order to bring quantum computer into a real practical usage. So in order to bring improvements in these speed components, as I said at the beginning of this presentation, we are bringing classical computation near to the quantum computation in order to improve the speed. Here you can see that we have 2 ways of including involving classical computation in a whole computation which involve both. The first one is real-time classical computation, which is inside the QASM, the Open QASM 3, so the quantum assembler language that we use to program our computers. And here we have some classical real-time components which help the quantum computer in order to perform at best. And also very important, this near real-time classical component, which is the Qiskit Runtime, which we introduced just from some of our quantum system during last spring. And during the Quantum Summit, we announced that the Qiskit Runtime will be available for all the IBM system. What's Qiskit Runtime? Qiskit Runtime brings classical computation near to the quantum hardware, and it seems to be really useful for some kind of algorithms, for example, variational algorithms. So as you can see here, you do your Qiskit program on your laptop, on your computer, then the program enters the queue of the quantum system, and once it enters the queue, the Qiskit runtimes takes control of the algorithms. It sends the quantum circuit to the quantum hardware. Then it takes the result of the calculation, then do the variation of the classical parameter, and then the computation returns. And only at the end of all the variational process, it returns the result. So with this kind of solution, we are taking away all the time of the latency time of the connection, of the internet connection. And in this way, we have been able to speed up our calculation by 120 times the number we used to have before, just with this classical involvement in the process. This is the Nature paper we published in 2017, in which we calculate the basic energy, the ground energy of the lithium hydride. It takes quite a lot of time to do this because this kind of calculation is a variational calculation. And so we have to go to the quantum system and then back, do the variation, and then return to the quantum system. So it takes several days. But with Qiskit Runtime, we have been able to do it in a few hours. So the time contracted by 120 times. This is our roadmap. As you can see at the bottom of this chart, you can see the hardware roadmap I already explained in the chart before. But here you can see several other lines, which are the components of our software stack that we are developing for different kind of developers. So we are addressing different kind of developer, not just the assembler developer. Let me say that here are called kernel developers. For them, of course, the circuits, so the possibility to build circuits is available. Since 2016, we didn't put all the years before. It is possible, of course, both using Python, so with Qiskit, and also with Circuit Composer, which is a graphical toolkit, very useful for the education. The step of this year has been Qiskit Runtime that I already described in the previous chart. And the next goal that we have programmed for next year are dynamic circuit, which means that I can interact during the execution of the circuit, just reading 1 or 2 qubits of the algorithm, and then depending on the result of this measurement, and I can interact with the rest algorithm of the algorithm that is already running. So some kind of the already known algorithms theoretically use this kind of approach, and in the next we hope to be able to empower our system and our software stack with this kind of capability. We are also addressing algorithm developers with libraries on several fields. Here you can see the 4 fields that we are addressing today are optimization, natural science, in which you have also inside you have high energy physics, quantum chemistry, and material science. Then we have finance, several algorithm developers developed for finance, Monte Carlo-like algorithms, portfolio optimization, and so on. And then we have machine learning. In particular, we started with categorization, so quantum supervector machine and other algorithms for machine learning. All these libraries are already available on Qiskit, so publicly available. During the Quantum Summit, we already introduced some kind of components that we are going to publish in the next years to support developer algorithms. So guys that are not working directly with the hardware, but are working to develop algorithms. So of course, the most important target is the error correction that we will begin to introduce, of course, when we will have enough number of qubits. But we introduced this concept, which is very interesting, of circuit knitting. It means that when the developer algorithms develops one algorithm, the circuit knitting try to decompose this algorithm, if possible, of course, in smaller execution parts. Then it executes all the different parts separately. This is very useful because long algorithms will introduce a lot of noise, but smaller execution will reduce the number of noise. And then the circuit knitting will recompose the complete algorithms in order to give to the algorithm developer the full result. Starting from 2023, we will also introduce modules for model developers for business, and of course with science is a more abstract way of programming. They are not interested in the kind of hardware, so they will match both classical and quantum computation. They will work with several kinds of algorithms in order to build business models or research models. For the moment, we do not have this kind of components because we think it's not useful until we will have error correction and enough number of qubits, but we will start to release this kind of component from 2023. So another important announcement that we did last month, regards the integrated systems. At the end of 2017, we announced IBM Quantum System One, which is an integrated system which includes the processor, the wiring, the cryogenic platform, and also the control electronics, all in one single object ready for the production. The Quantum System One has a limit and the number of qubits for processor. So the Eagle processor we announced this year is the last processor that can run in a Quantum System One. So we announced the development of a Quantum System 2, which will be able to manage processor with more than 127 qubits. We are developing this kind of platform in partnership with Finnish enterprise which manages cryogenic apparatus, which is Blueforce, and we are working on systems that can be modular, as the one that you can see here developed by Blueforce, and this is just a rendering on what will be the Quantum System 2 that will be available in the next year, ready to host the Horse-Gray processor, which will be the processor that we will have next year. So aside to the technology and to the software news, we also are developing a really wide network of research centers and enterprises and universities that work together with us. We surpassed the number of 170, and we are working on a lot of use cases with them. For example, just looking at the first line and the first column, which are the partners, so the highest way of becoming member of the IBM Quantum Network. Here you can see, for example, JP Morgan Chase. With them we are working on the pricing of the European stock options. We are working also with, for example, ExxonMobil, working on thermodynamical variable. We are working with Daimler in order to analyze the reactions which are going on inside batteries in order to build batteries with a higher autonomy for electric cars. And all the rest, of course, I'm not going through all of them. Very important are the national partnership that we are developing with some countries all around the world. In particular, here in Europe, we have the partnership with the German government, which is managed by the Fraunhofer Institute. In the last spring, we have seen the previous Chancellor, Angela Merkel, which participated to have the event in which we presented the German system, which is the Quantum System One, which is installed for the Fraunhofer Institute in Germany, in order to serve the small and medium enterprise of the German market. We have similar agreements in Japan, and last month we also announced that a similar agreement has been done with the South Korea on the Hyonsei University, that will manage the system in Korea. This is my last chart. It's just a chart to show you how you can interact and how you can leverage all the tools that we are giving open to the community. The first one is the Qiskit textbook. So if you go to qiskit.org, you will find a really deep textbook about quantum computation, which has both the theory and also the exercise that you can run on real quantum computers using Python. The second, you can explore quantum computing website from IBM and also Qiskit in order to have a look to the circuit composer, so the graphic tool for the program part, and also to Qiskit to look at the tutorials and a lot of materials that you can use to develop your use case. Then we also release a couple of certifications. So we have Qiskit Advocate certification and Quantum Developer certification, which are openly available and you can apply. On YouTube, you can find a lot of videos. You can also find the videos of the Quantum Summit. So if you are interested on what I've said today, you can have a deeper look on this kind of presentation video. Then we have research and education programs. So if you are doing research on quantum, you can apply to have access to more powerful quantum computers and dedicated quantum computer for your lessons and for your research. So that's the end of my presentation. We have a couple of minutes for questions. Thank you very much.
Thank you. Thank you, Federico, for this great overview of what IBM is doing in the quantum realm. So let's see if we have questions. Okay. So in the meantime, let me ask you just a curiosity. So you said that you're going to have dynamic circuit in the future. So as far as I understand, let's say intermediate measurement on the system, and do you have in mind some application, a short-term application that will benefit from this new feature, or?
I don't have for the moment any specific use case, but it's something that will allow us to do interaction, which is for the moment quantum algorithms, you know, is quite a black box. So the possibility to have an intermediate measurement and the possibility to interact, introducing other qubits, of course, and other gates, it would be a great improvement on what can be done on a quantum computer.
Okay, thank you. So some questions from the chat. If you can tell more about researchers and education programs, so probably how can you enter in these programs? Okay,
so these are two programs. I can then share, of course, the link to which you can apply. It's quite important to have a research that is already been developed to some level, because as I've already said, we have open access systems that you can leverage, so you can work on them. You can work, of course, on simulator, also simulators with noise. So after all these kind of studies, if you have publications, also archive publication, you can put them in the application form, and then we will review, IBM Research will review your application and give you access. The systems which are available for the quantum program, for the researcher program, are system of 7 qubits, so just a couple of qubits more, but one of the important things is that they are reserved for the researcher, so they are not public for everybody, so you will not face all the queues that you find on the publicly available one.
Okay, thank you. So another one from the chat. So David is asking if it's possible to get technical support from IBM when you deploy the code for our algorithm, quantum computing algorithm.
So, well, of course, you can ask to IBM. The better thing to do, also from my experience, is to leverage on the Qiskit open source community. On Slack, you can find a Qiskit channel with really a lot of developers, an open source developers that are working on our platform, and they are really efficient to give you support if you have some problems, some issues. Of course, IBM research persons are dedicated clients, and so they take some more time. But the Slack channel for the open source community is great for this.
Okay, probably there are more questions in the chat, but I think we can stop here, and if you want, you can answer directly in the chat. So yeah, thank you again, Federico. It was a pleasure to have you here. And